Professor Manimaran has already joined from VIT Chennai, and he is one of our esteemed executive faculty partners, and he has been associated with FOSSEE IT Bombay since long time. And he has guided the maximum amounts of students who join us as semester-long interns and summer fellows. And so over to you, Professor Manimaran. You can start the session.
Okay, let me start my session now. Thanks for introducing me. Thanks to Palman. I've been with CFD FOSSEE IT Bombay for quite a long time. And Madam has requested to give me a talk. So I prepared my talk aligned with this modeling the multiphase flow in OpenFOAM. Myself, Professor Manimaran, I'm from School of Mechanical Engineering at Vellore Institute of Technology, Chennai. Anyway, throughout this presentation, I'm just going to give you an overview about what is a multiphase flow. Anyway, I'm not a full expert user in multiphase flow. So whatever I know, just I'm going to share with you. Okay? And whatever I did, I just share with you. So let me go through the contents of my presentation. So briefly, I'll be touching about introduction. I found out that yesterday also you had a multi-phase flow session, the same topic. I think already on two-phase flow. I think in the afternoon yesterday. I think you would have learned a little bit about introduction. Let me brush up a little bit about that and then go through the applications of multi-phase flow and some categories of multi-phase flow. How do you approach solving the multi-phase flow problem in OpenFOAM? What are the simulation models available in the OpenFOAM for different categories and applications? And let me give you a quick glimpse about the tutorial available in OpenFOAM, how to do it, and how is it different from other flow like incompressible flow. Let me give you a quick distinction between them, and then followed by literature. What are the literature available on multi-phase flow in OpenFOAM? The recent literature available in the. So let us also discuss about that. And finally, I'm going to talk about the research what I have carried out at VIT Chennai. Thank you. So let me go to the introduction. So of course, you may know that multi-phase flow. From the name itself, you know that three phases. You may know that, or it may be four phases as mentioned in the slide: oil, air, water, and solid for petroleum extraction application. So this is liquid kind of flow. But if you see here, gas, solid, and liquid, three phases. And in this slide itself, you can see that. You can see the applications or the processes involved in the multi-phase flow. For example, the transition of solid to liquid or liquid to solid, slurries, food processing industry, and emulsification processes are predominant. And in the transition between gas and liquid, condensation, boiling, spray cooling, dryers, refrigeration, and biological flows. And in the transition between gas and solid, you can see fluidization, pneumatic transport, coal burners, then cycle separators, and some biological flows also come in this picture. So let us see about the applications. Okay. It has got wide applications in process industries, refrigeration industries, air conditioning, petroleum, oil and gas, food processing, automotive, power generation, metal industries, metal extraction, and so on. The phenomena includes here mixing, a particle-laden flow, and then the reactor in vessels like involving the gas dispersion and floating particles, and suspension in an agitated or still vessel. Then another good example is a fuel injection in the engines, in diesel engines or petrol engines, of which has to be the tight norms as per the Bharat State 6 for reducing our reduction of emissions. And so on. And also another example is a bubble column, which I also show animation about that. Next, coming to the category. So here, different categories as we already seen it in the before slide. The interface between the phases are influenced by the motion of the fluid. For example, a water flowing through a packed bed of rocks. It's a single phase flow. Okay. Multi-phase flow regimes are typically grouped based on immiscibility into categories. Like, For example, gas and liquid, which are naturally immiscible. It cannot mix each other. And immixable liquid flows, for example, petrol and water. Then gas solid flows and liquid solid flows. In a multi-phase flow, one of the phase is usually continuous. We call it as carrier phase. For example, if you take petroleum taken in a ship, which is getting mixed in a seawater is carrier phase, this continuous media, and the other phase that is the petroleum here is dispersed in it. So this is called as dispersal phase. Next, coming to the categories continuation, okay, the gas liquid phase are further grouped into many categories depending upon the distribution and the shape of the parcels, namely like, for example, that's spelling mistake, bubbly, BUBBLY, slug and annular. You'll also see some animation videos about that. What is the bubbly flow, what is slug and annular flow. Next slides. Another broad classification of multiphase flows are homogeneous and inhomogeneous. So how they are different? Homogeneous means all the phases are moved at same velocity and same flow field. There is no velocity slip between them. That means the main distinction is that both the phases move at the same velocity. Whereas in inhomogeneous, each phase has its own flow field. There is some velocity slip. There is a difference in velocity between the two phases. That is called inhomogeneous type of multiphase flow. So next we will see the flow region in horizontal conduit like pipes, investigating bubbly flow and slug flow. So I think in this slide you can clearly see that animation of showing the bubble flow and the slug flow. So bubbly flow, it represents the flow of discrete gaseous or fluid bubbles in a continuous phase. The homogeneous multiphase models can be used for this flow region. So you can see that there is some bubbles. Multiphase flow, you can see some bubbles, very small bubbles. And whereas in a slug flow, it's characterized by the flow of large gas bubbles. So you can see large gas bubbles, which you can see in this cross section of the pipe. Then coming to the different flow patterns in this bubbly plugin. Okay, so here there are well-defined literature available in this, starting from bubbly flow, plug flow, then stratified flow, then wavy, slug, and annular flow. So bubbly, so see here, small bubbles are present in the liquid. Whereas plug flow, you can see a slightly bigger bubble. Then there is some stratified flow, that is called a distinction between gas and the liquid. You can see the layer being formed, strata. So it's called stratified flow. Then again increasing the amount of gas, it results in a wavy flow. You can see some waves are formed in the gas region, and the liquid is below, and then followed by slug flow, then annular flow. So annular flow, you can see that the liquid is getting clinged onto the walls. So it's in the annular region. It's called annular flow. And further increasing the gas content or flow rate of the gas, you can see that spray or mist or dispersed flow. So this is a typical flow pattern for a gas liquid phenomenon, from bubbly to plug and stratified, and then wavy, and then slug, and then annular, and then to spray. So next we will see in a chart, in a graph, how do they vary between the parameters. So here we have two parameters mainly. If you see here, we can see there is a x-axis here and the y-axis here. So it's called the mass flow of the liquid and mass flow of the gas. So depending upon the flow of the mass of the liquid and the gas, the region can be formed between different types of flows. So here you can see a stratified flow is available within this 200 kilogram per meter second of the liquid phase and 2 kilogram per meter second of the gas phase. So similarly, you can see that wavy, it is on the top of the stratified, whereas accompanying the stratified is a slug flow on the plug flow here, and then annular flow on the top if you increase the gas flow rate, and further we have dispersed flow like a spray. Further increasing both the liquid and the gas, you can see it is in the form of froth and the bubbly flows in the bottom. So this is like merging of the regions. by increasing both the liquid phase and the gas phase. So it is well available in the literature. You can see many people have worked on it. So like convective boiling and condensation is also explored by John G. Collier and John Armstrong. And you can see this literature by Mandan and Gregory. They have formed a map for horizontal flows in the pipeline. So they come up with non-dimensional numbers like this: density of the gas to the density of liquid, and like air and water, and atmospheric temperature and pressure. And with that, they can distinguish the parameters between the flow. So here is a good example. You can see here on like animation picture, like you can see bubbly flow and then slug flow, and then churn flow, and then annular flow, and then fully annular. So we can see the slug flow here. You can see bubbles and then slug flow on the right side, and then further marching towards the annular and the. So here you can see in this slide the distinction clearly, the bubbles, then plug flow here, and then you can see the annular flow on the right side. So this is a clear indication. So you can see transition from the bubble, like gradually increasing in size, and then suddenly bursting out into a plug or a slug flow, and then formed by annular flow, and then churn flow, and so on. So these are the different flow patterns in the vertical pipes, which is given by Hewitt and Robert. Again, they formed a non-dimensional number or a number that is specific for differentiating the liquid and gas flows in vertical pipes. So now coming to the approach, how do we solve the approach of the multiphase flow? So as we know already in fluid mechanics, we know that Lagrangian approach and Eulerian approach. Lagrangian stands that it relates to the phenomenon of tracking the moving points or the particles, such as the tracking moving vehicle on the road, like individually tracking the particles in a flow. That is called Lagrangian type of approach. On the other side, we have Eulerian approach. We have two fixed points or any number of points in a field where we just count the number of or measure the parameters like velocity or the pressure and so on. So here we see that counting the number of vehicles, type of vehicles, and the speeds, like in sitting in a place in a like what the traffic inspector do on the road. It is like the Eulerian approach. So we have these two approaches available in the OpenFOAM also, and we will see what are the simulation models available in the next slide. So in the coming to multiphase flow in this OpenFOAM, we have Euler approach. That means for gas and the liquid, both go following the Eulerian approach. And then another classification is that one is Eulerian, another one is Lagrangian. That the either liquid or gas can be Lagrangian, and another continuous phase may be modeled in the Eulerian approach. Under Euler approach, we have volume of fluid, okay, model, and then Eulerian model. Whereas under the Euler and Lagrange approach, we see that deep, like discrete particle approach, like spray foam, MP, PIC, particle in cell methods, multiphase flow. So it is available in the OpenFOAM also. So whereas in the VOF model, we are familiarly using VOF, that is the interfoam model, which I will be showing in the next few slides, how to use that and so on. And then in the Eulerian model, we also have two-phase Euler foam. This is available in the OpenFOAM from the beginning. So in the next slide, you will see what are the different solvers available in different categories. Interfoam is for two mixable fluids with a dynamic mesh approach, whereas multiphase interfoam is for the different fluids like oil, mercury, water, kerosene, whatever it is. If you have multiple fluid liquids, you can use that. Inter-isoform is a special type of solver for interfoam with solving the iso-advector method. And over-intermittent foam is like overset grids, if you have used overset grids for the dynamic mesh application. Whereas another one is compressible interfoam is for the compressible version of the interfoam with heat transfer. Then compressible intertube foam for the dynamic mesh application. For a mixing application, we have got intermixing foam for three fluids, two mixable and one immixable. Then two liquid mixing foam is for two mixable fluids, and so on. And then multiphase Euler foam is for multiple mixable fluids using Euler approach. So next, coming to the phase change problem, for example, cavitation. Then we have cavitating foam, which is for two mixable fluids, especially for cavitation problems, employing the homogeneous equilibrium model. Then interface change foam is for two mixable fluids using VOF volume of fluid method by Schneider and Shaw multiple occurrence. Then cavitating dim foam for the dynamic mesh application and so on. Interface change dim foam also. And then over interface for the dynamics with the oversight grids for dynamic mesh application. So another phase change general application like condensation and evaporation, we have intercondensating and evaporating foam. This is for two immiscible fluids. Phase changes during evaporation and condensation is taken care between the fluid and its vapor phase. Next, we go to the dispersed phase of modeling by Euler approach. Like multiphase Euler foam is for multiple mixable fluids using Euler approach. Then we have dispersed Lagrangian type. One is DPM foam. It's called discrete particle number. One fluid and particles are taken care of. Particle-particle interactions resolved explicitly. Direct approach. Next one, we have MPPIC foam, that is particle in cell method for multiphase flow. This is for one fluid and particles, dense particle cloud. It is not a single particle, whereas in DPM foam, every particle is taken care. Whereas in MPPIC, dense particle cloud, that is combination of particles. Selected number of particles are taken within a parcel, it is taken like a particle-particle interaction. It is a simplified approach of the DPM foam. Then we have DPM dim foam, that is dynamic mesh application. Then MPPIC dim foam for both of them, dynamic mesh application. Then under dispersed and drift, like slurry model, everything we have like plastic dispersed phase, heavily dispersed phase, we have a drip flux foam. This is especially for applications like muddy flow or plastic flow. So next, we have multi-component phase, like we have many reactions and species involved in like of different phases. We have simple reacting parcel foam, so which is take care of the reaction also. So that steady state multi-phase particle clouds. Then reacting parcel foam for taking care of transient multi-phase particle clouds. So simplified version. Then coming to the spray application, we have spray foam and spray dim foam or fuel spray combustion with dynamic mesh application. So let me show it in the tabular approach, the distinction of those things. Okay. So if you see, generally we would have used interfoam, intermixing foam, multi-phase interfoam, and two-phase oil foam. The distinction, if you see here, heat transfer is not present in the interfoam and the intermixing foam. And then compressible fluid is taken care in the two-phase oil foam. And number of phases, if you see here, it is 3 or more than 3 for the intermixing and multi-phase interfoam. Then continuous phases and dispersed phases are taken care in appropriate solvers. Fluid properties also is shown here. Okay. And so OpenFOAM handles these header files separately for these solvers. So surface tension is taken care in all the models and turbulence also. So I think you would have seen some equations already in the yesterday's presentation. Generally, typically, let's say the transport equation of a multi-phase flow, we have to see the nomenclature first. Phi. Phi stands for general phase variable, mixture variable in mixture mode models, and alpha. Like alpha, you know that volume fraction of the phase. This is 1 for liquid or was 0 for air and so on. Next, we have a density rho, then P underscore rho GH. This is calculated like P minus rho G X, that is hydrostatic pressure subtracted from static pressure. Then dispersed phase with lower volume fraction, carrier phase with higher volume fraction. Then particulate loading is defined as the mass fraction ratio of the dispersed phase to that of the carrier phase. So the equations you can see here, transport equations here, like you see, first is the unsteady term or temporal term. The second one is the advective or the convective term. On the right side of the first term is you have the stress term and the source term. So all these equations are integrated into the OpenFOAM in the C++ framework, and they are solved iteratively. So here, the momentum equation you can see here. So the alpha, if it is one, it's a like continuity equation. Alpha is equal to velocity as the momentum equation. You can see here it is being replaced here from alpha. So not alpha, sorry, phi. Alpha is the volume fraction. Phi, the phase variable, if it is one, it is a continuity equation. And the phi is equal to V stands for the momentum equation, the mixture model, just shown here. So now let's take a look at some of the solvers available in the OpenFOAM, like Interfoam, solver for two incompressible isothermal mixed fluids, which is using a volume of fluid phase fraction based interface capturing approach. So this model is especially made for capturing the interface. How does the interface behave? For example, if you see an example here, the slide here, the water flowing over a weir. How does the shape of the weir take place? This is very essential for civil engineering applications. So here the momentum and other fluid properties are the mixture type, and a single momentum equation is solved. Turbulence modeling is generic, either you can use laminar, Reynolds averaged model, and large eddy simulation. Next we come see a DPM foam, which is specially for the dense particle flow simulation with a volume fraction of 10% or higher, particle is more than 10%. This solver uses a functionality of particle clouds and collisions, takes out collisions, particle-particle interactions. So you would have to give some drag force. Some models are involved already by default, and you can also weigh the constants involved in that drag force by each particle and so on, the shear force and so on. This is a transient solver for a coupled transport of a single kinematic particle clouding including the effect of volume fraction in the continuous space. We have another Lagrangian, that it's a spray foam. This is especially for the predicting the behavior of spray, such as optimizer, the discrete phase model, and this like further breakup also. The spray breakup is also identified from this solver. So there may be constraints in the mesh resolutions. It may not be entirely predictive. The accurate submodels may be needed for drop breakup, atomization, drag, turbulence interaction, vaporization, breakup, and collision, coalescence, spray volume. So different submodels are available, which you can avail from the header, solver in the OpenFOAM. And the next one we have the MPPIC, like multiphase particle incident method. It's a Lagrangian solver, like particle tracking capabilities. It is there for modeling particles in continuum. This is simulating the solid phase as parcels and to represent the collisions without resolving particle-particle interactions. So it is not resolved to the particular line. Only the collisions representation is being solved with like a cloud approach. It's taken like a cloud, some cloud of particles it is taken. It is identical to DPFOAM, but without the collisions. The collisions is not taken care in the MPPAC. So I think most of you would have installed OpenFOAM, and I think you would have seen many folders like this, like stability foam, compressible interacting foam, and so on, interfoam, and so on. So, what are the distinction between the general, like single phase flow and the multi-phase flow? So let me show it in this case of OpenFOAM. With respect to OpenFOAM, there are two things are, I think when you're running the command, the set fields, and the another one is the when you're defining a variable called alpha or alpha lambda. Okay. So the set field stick is nothing but it's the facility to set the field which is water, which is not water. For example, in a region where you want to define the water or water, then you create a box for that, a simple approach, and the set it equal to 1. Alpha is 1, that means water. By default, you put alpha is 0, that means it is gas or air. Something. So this is being defined in the set field stick before you call the application, your solver like interface. And remember that you should have the block mesh ready before, after which you should set the set fields. Then another, which is very important variable in the to be considered the multi-phase flow, it's nothing but alpha. I already mentioned it's a volume fraction. If it is 0, it may be purely gas. It may be it is purely liquid in the case of 1. So it has more dimensions. It's a ratio. So you can see how it is being defined here. Like see here, wall at the wall, how it is being calculated. Boundary conditions are given 0 gradient, and atmosphere is inlet outlet, and default phase is type empty. So this variable alpha.water is the file available, should be available in the 0 folder before you call for the application, like any solver like interference. So I think now you would have understood some idea about the models and the multi-phase flow approaches in OpenFOAM. So now I'm just going to go enter into the literature. Some of the literature we see recently published where OpenFOAM has included multi-phase flow in the research literature. So I think just I'm going to list a few so that you can get some interest about the multi-phase flow. So here I think this picture may not be clear, but I think it's a horizontal pipe on which steam is passed at the top and water is passed at the bottom. So it's a typical application in an atomic power reactor, which includes a condensation induced water hammer case. Suddenly, if the water is being pumped, the hammering can happen, water hammer. So this is followed by a sudden shock formation. So this is solved by using a reacting multiphase Euler flow by this researcher Abram et al. Maybe you can take a look at this UI for further reference. And especially it is at they belong to Hungarian Atomic Energy Research Institute, so they researched it. They can find that you can see the bubble volume. You can see the bubbles are formed at the inlet, and then gradually it is getting the bubble burst is happening. So they want to design a pipeline with that, which pipeline can give the good prediction about the water temperature rise, the steam water co-current stratified flow. So I think if you see at different time intervals, water volume fraction is mentioned here, temperature. So they can come up with the design using this solver, reacting multiphase order. So in the next literature, they use MHT interfoam, MHT, magnetohydrodynamic flows. This is especially for that like if you have a magnetic field in the flow, like fluid, like mercury, where it is conducting, magnetic field is predominant in that. So they are calculating using this parameter called B naught. They impose magnetic field, and then they are seeing the flow field around that flow in a container. Okay, in a container like this. So I'm just giving an example about the flow region with the helium bubbles are being raised in the lead lithium eutectic alloy. If you can, like, if you have a material like this, the critical condition for multiphase numerical models, they can easily predict with a solver called MST interfoam, which is for two incommensurable isothermal immiscible fluids using V of interval. So the results are promising with a discrepancy of less than 10% compared to their experimental validation. So they can identify the bubble where it is formed with the boundary imposed boundary condition, and then they also have a plan to identify and select suitable benchmarks for other multiphase industries. They will compare the result with the literature and experiment also, and different codes. Like not only MST interfoam, they also used CHT multi-region foam, where they have you have conjugate heat transfer, right? In the heat transfer problem, they also use that one and compared this with the MST interfoam. So in the next literature by Alan Islas, et al. 2022, they've taken a 20-liter vessel in which the coal dust is being dispersed in a vessel. So they want to simulate the turbulent dust dispersion in the vessel here. The coal is being present here and it is being dispersed in a 20-liter vessel. They used a coal chemistry foam. It's a multi-phase transient solver for compressible flow. And the interaction between gas and particles is modeled by Euler and Lagrangian approach. Using the discrete particle method is also used to reduce computational. So they can come up with different times how the flow of particles taking place, whole particles in the simulated condition inside the vessel. Next is a very interesting application. Like if you see in this picture, it's an ocean engineering problem, marine application, where they want to capture, okay, the interface interaction between the water and the net of the inside the a sea wave, under a sea wave. So this interface capturing approach is being solved by using interFOAM solver, which is that we have polymer fluid equation. Uh, they have extended it to use Gauss Van Leer scheme with the first order implicit Euler scheme for time integration. The 6 degrees of rigid body solver is used with interFOAM using overset grids, and it is VOF is used to capture the multiphase fluid dynamics, and they integrated with this with the screen model and mass spring method for the flexible density formation. And for simulating this mooring, you can see the cable that has been tethered to the bottom. For mooring, they use another software called Mooredin and endo beams for structural deformation. They also employed immersed boundary method to capture the interaction between the fluid and structural components. So from the results of the interFOAM, they've taken it to the other like Mooredin and the immersed boundary method. And they could see, because of the interaction between the fluid solid interaction, the wave surface phenomena is being shown here. Wave surface phenomena is being captured, and then they could analyze that at different wave conditions. So here is another extreme of the application where it's a shock flow. I think many of you would know the compressor flow, the shocks will happen if the object is going at very high speed, like sonic speeds are more than that. Subsonic and supersonic, crossing the sonic region and then supersonic region. Typically in a wedge application, when there's a driving flow and the flow is being driven, so you have a high compressible, highly compressed gas here and low compressed gas. Suddenly you will see a shock will be formed like this oblique shock when the object sees the, like beforehand, the to balance the equilibrium, the shock is being formed, and you can see that single phase DBNS foam, they've used it to solve the gas solid two phase flow in a two fluid model framework. So essentially, it is not just a flow of air or gas; it is flow of air with dust particles. So the dust particles, they want to simulate it. Like if you have seen, like if the bus is going very fast, behind the bus you see the dust is being carried away. So for this, they want to simulate it. So like a shock is the bus here. The shock is moving in either in a shock tube experiment or in a flow past a bench. So they want to simulate the dust how it is being carried away. So they use a DBNS foam to the primary carrier gas phase, the dispersed solid phase, like the dust particles are being handled here, and using multiphase Riemann solver for shock applications. So typical, I think Riemann solver is used for compressor flow. They use it for this method. Next is the cavitation problem. So you can see here, and the airfoil is moving at high speeds. You know that low pressure region is formed, high pressure region is formed. So they want to identify the cavitation and then identify the vapor fraction. So for that they used a polymer fluid method with a two-phase change. Polymer fluid method. Okay. So they used cavitating foam, and the calculation efficiency in the cavitation problem. They also extended it to the pump actually from the dissipation of numerics. Okay, they found that changing the grid will solve the problem, and then considering cavitation mass transport, they modified the momentum equation by introducing surface tension and adding the artificial convective flow to the phase equation. So they have employed a different way, extend the VOF model further to model it in an appropriate way to match with the extended model. And here is another interesting example of a horizontal gas liquid pipe. Okay, in a pipe. So you have a gas flow, as we already see in the initial slides. I've shown you the bubbly flow coming from bubbly to slug flow, and then going to the annular flow and so on. So in a horizontal gas liquid pipe, especially this is an application with respect to the rocket engine motor. You have a high-speed gas and interacting with the liquid fuel. So this is being solved in the case of interform with continuity momentum equations of two-phase immixable fluids. Then the continuum surface force model is used to represent the effect of surface tension as a continuous volumetric force acting within the interface region. So they could find out the waves, how they are being formed, interface. So the continuous surface force is very important to be identified. They can identify from the simulations. This is also another interesting study in a civil engineering approach. The interform is being used for identifying the coastal and offshore engineering applications to avoid the tsunami in a rheological case. So they use rheological model linked it to the, like they use OpenFOAM viscosity library. They added some rheological models, and they use a multiphase interform solver to model the immixable sliding granular flow interaction with water. So they see that different levels, how is the level of like granular flow in the unmixed phase. And this is like a typical application of floating buoy, like you know that wave energies converter models. You might know that because of the wave motion, the sea wave motion, the buoy will go up and down, and from that the energy can be converted. So for that they used a water gauge to measure the free surface interaction. How does the wave? So you can see the wave approach. They used a different overset grids to model the buoy here, and then the buoy is going up and down. They used Euler and Lagrange particle cell model, and to variety of complex wave interaction in both 2D and 3D domains. So they could see that this use of overset mesh enables the deformation of mesh in the narrow gap to be avoided. So the overset mesh is very useful in the case of interform solver, typically in these applications. So next is catamaran. I think you may know that it's like a boat. Typically, the fishermen use the catamaran shape. They used it. They want to identify the sensitive and critical slamming phenomena. So to identify that, they use this interform and over intertem dim form. That is dynamic application. And typically, they want to modify the hull of the catamaran. So they use ventilation pipes so that stability can be achieved, and to discharge these, like whatever water collected on the top. So they have connected different impact velocities, 12 case studies, and they also change the hull to amended case and compared to the standard case. So this is another study where the OpenFOAM is being used to develop a new solver called two-phase intertrack form using arbitrary Lagrangian and Euler interface tracking for accurate tracking of fluid phase in deforming solution. Okay, especially for two-phase flow problems involving surface active agents, surfactants, where there is a variable surface tension force and very sharp boundary layers. So they developed their own solver, and they compared some results with the literature. And here is another multi-phase interform for simulation of waves by high mobility submarine landsliding problem. It includes slide flow over a slope, impulse wave generation, wave dispersion, wave propagation, breaking. So they found out that including the turbulence with the buoyancy term from the case of multi-phase flow, it could be for this only the flow can be accurately calculated. So they compared this with the experimental condition also. I think this is the final slide in the literature, and this is typically energy storage by fluids. So it's a thermal destratification problem caused by continuous bubbling. They developed a new solver called interthermal destratification foam with energy equation, the existing solver, to solve the heat transfer problem. So the investigation of bubble dynamics for various fluid properties they showed that the interfacial tension force increase the time for bubble detachment and bubble diameter also. Okay, so I think by seeing all this literature, I think we can get inspiration about the usage of multiphase flow in OpenFOAM. And next, I want to show you some of the research that I carried out here in Chennai, especially in the area of multiphase flow. So typically, this you see, one of my postgraduate student, they're interested in developing underwater vehicle. So they developed their own design, which can go into the water, dive in, and come up. And the acknowledgement goes to Vivek and Manjunatha in 2018. So they developed an underwater vehicle and for inspecting immersed pipe in a water. Okay. So they developed different configurations of the robot, and they're from MTech Mechatronics, and they built different components like this, like if you see gripper and support arm, then robot body, then propeller base. Especially the body houses the components like battery and some circuit components for controlling uh, the propellers here. So they have successfully built a robot, and the problem is that they found out the heave motion, sinking speed is very limited. Surging is also very limited to 1.1 meters per second. It's a very slow approach based on the availability. And you can see the video here on the top right. The rover, underwater rover, is being controlled by the remote way with which is interacting with the sensor on the top of the robot here. So the peculiar thing about this robot is that they developed at a very low cost. The total cost is coming under 10,000 rupees. Maybe it can exceed 1,000 rupees more now. And what I want to show here is that the motion of this robot, how it can be simulated in the OpenFOAM. So for this, anyway, including all the grippers and propellers is very difficult. Yet, my study started with a simple numerical wave tank, where the wave is being started in the one side, and the wave propagates in this way, like you see in the top, and the free surface, we can see how the wave height is going up and down. So it can be captured, and we compare the experiment; it's almost matching. Next, we introduce the ROV. How does the robot behave with a wave imposed on the top, like a traveling wave? So for this, the interface has to be captured. So we have captured the ROV with the obstacle and without the obstacle. What is the interference in a moving case? If you see, the next study is about the hydrodynamics involved in that. What is the lift involved by incorporating the wave and without the wave, and with the obstacle, without the obstacle, which we could explore that in using the simple interfoam solver open. And the same object, if it is a structure, if it is a bluff body like a square or we can see it is like a prismatic object. So what is the change? How does the Fourier spectrum of the wave change? Everything we explored, and in a three-dimensional environment, this one again using interfoam solver. So the grid has to be reformed near the boundary, the permissible limit. So next application is here is the wave energy converter, which I'll explain you. Like typically put a horizontal pipe under a wave. You know the wave is actually if you see ups and downs, you may know that. But actually the velocity under the wave, one may consider that it may be taking like up and down. But actually it is orbital. The velocity is orbital in nature. That means it is. If you see the velocity vectors here, it is like orbital. It's like a rotatory motion of the fluid particles under the wave. So we are going to use that and use that by allowing the flow to go through inside a pipe with an aperture, like a nozzle, acting like a nozzle. So if you see this during the crust and the trough condition, there will be a slight flow of fluid across the aperture where this power can be used. This energy can be used or conserved, okay, with the help of a small propeller. That is our idea. So we found out by by doing simulation with interfoam, we could see that at different time instants like 12 seconds and 12.5 seconds, you can see that the flow is like oscillating flow. The velocity on the right side it is higher here, whereas in this 12.5 meters a second, the flow on the left side it is higher. So it is like oscillating. So already there is turbines are available for handling the flow conditions based on the size available. So typically we can explore these kind of applications using OpenFOAM with using a simple interfoam solver. So we have compared with the different wave heights and different orifice diameters, 1 millimeter and 2.5 millimeter by refining dimension, and found out the efficiency. So we found out that orifice a very lower, like 1 millimeter orifice compared to 2.5 millimeter orifice gives a better efficiency. Coming to the next application, where again interfoam solver is used, we can see it's like a upward pipe, vertical pipe, where the flow is rising. It's not just a water flow; it is both water and air. So here, as you know, air is flowing upwards, but the novelty what we have found with the pipe here is they've introduced a swirling flow at the inlet at the bottom, and we found how does the not swirling flow, sorry, convergent pipe here, slightly convergent. If you have noticed it, it's a straight pipe here, and it's a convergent pipe here, right side, and a slight convergent of about like 4 degrees is given to understand the flow happening, whether the flow is being converged and the bubble is being removed, or the bubble loading is being reduced. So that we have introduced by finding with the Q criteria. We have found out Q criterion approach to indicate the vorticity involved in this flow, and it is shown on the bottom right. So we have seen that convergent is with this. We can see that uh, bubble is getting collapsed easily. Okay, with help of slight convergence at the exit on the tops, and could also found out the fraction, or the volume fraction with respect to time. We tracked it and we found that the same. So next application is like an oscillating water column, where it's like a buoy. You can see that buoy, floating body in seawater. Usually it is rectangular in shape, but here I made a slightly trapezoidal, a converging effect again, to explore the, again like a nozzle on the top of the chamber. You can see that the traveling wave compresses the air inside the oscillating column, and the air is being sent out of the top, or like a nozzle through a nozzle, where that air can the flowing air can be used to track the flow and then capture that energy. That's our idea. So at different time intervals, you can see the different hydrodynamic pressures acting inside the water column here, and here the geometry is being slightly modified for a trapezoidal geometry, and then we explode it compared to the rectangular case. So again, we have coupled this oscillating water column in a floating environment. So previously this was a fixed environment. Now we made it as a floating environment. The oscillating water column is now floating. And then next one we have another wave energy converter called BBDB. BBDB stands for backward bent duct buoy. So again, it's a floating body. So we could see the capture width ratio, comparing the placement of the floating oscillating water column and the backward bent duct buoy in both regular and irregular wave environment. This is available in the OpenFOAM in the interfoam solver. So we could see that in a irregular the capture width ratio for the you can also see the capture width ratio for different. Okay, we analyzed it for the different grid sizes also. So another interesting flow using multi-phase flow in the industry is that like in oil and gas lines, oil and gas transportation, like pipe carrying gas or oil from one country to another country. So you may see that during transport, the temperature fluctuations may happen, and because of that, gas can even be condensed, or water can, or oil, or whatever it is, it can be condensed also. So this is a main problem in the transportation sector. So for avoiding that, they will be using a bent duct, like undulated pipeline. How to remove that, like water is being or liquid is being collected on the undulated pipeline on the bottom here. How to remove this in an efficient way? So that's the problem here. So typically they blow the air on one side into this water in a pipeline, and you can see like water will be going to the other end. You may know that. So now instead, we could also see we want to have it converted back into the gas. So for that, we are just trying to allow the swirl flow instead of axial flow, and then we have compared it with the axial flow case here. So in the swirl flow, the water fraction or the volume fraction is being transported easily. The volume fraction contour showed that the water can be easily carried away by the swirl flow. So next we have another application using intercondensating evaporating foam. The typical have a humidifier on the right side, increased it by means of heating the plate. So here again, we have compared the bubble column humidifier between the axial flow and the vortex flow at the bottom. Boundary condition we have changed. So the airflow is being modified into a swirl flow, and identify the fluid interface capturing and bubbly flow also using multiphase Euler flow, maintaining the same flow rate of the air. That's the important thing. So here we can see that in the vortex, the interface is lowered, and efficiency of the evaporation also is better. So next one, these are the typical applications which I explored using OpenFOAM, like exploring the slug flow in a microchannel and also droplet flow. So you can compare the difference between them in the screen here. How does the slug flow happen and the droplet flow? Slight deviation only. This is characterized by the velocity of the air as well as the velocity of the liquid or water here. So the transport of the bubble or the slug or the droplet, the transport, if you see here, it is very interesting, and it is of very scientific. It has got various scientific applications in the industry also. So if you see in an inclined surface, that was a horizontal surface in the previous slide. This is an inclined surface. How does the bubble droplet traverse an inclined surface? So for a contact angle, like if you see that it's a hydrophilic surface, so you may know that less than 90 is hydrophilic, above 90. Like mercury is hydrophobic. So we have taken a 120-degree angle, contact angle, and then we simulated this, the simulation of the droplets in the inclined surface. And also we have compared it with the other boundary condition, where you can see that flow rate is increased, and you can see that movement of that slug alongside down, like a dancing flow happening, and it can suddenly jump into rapidly burst into a different kind of flow, like exploring a new science in the multiphase flow. So that is the beauty of using the solvers here in simulation, OpenFOAM simulation. So we have a better control of our time as well as understanding the physics and everything using this OpenFOAM. So we can see that multiple small droplets getting accumulated and traveling as a big ball slug downside down. So next application is my favorite application, which I almost explored, like using a vortex tube. It's nothing but a small horizontal tube where the compressed air is sent in tangentially, and on one side we have the small aperture at the center near the inlet, like here, cold air, where cold air is coming. On the other end, a valve is being blocked so that flow can leave only at the periphery, so the hot air is coming on the other side. So the same simulation is being carried out in OpenFOAM using sonic foam, which is a compressible solver. But we want to analyze the presence of moisture. That is two-phase flow. Moisture is nothing but water vapor. So we want to simulate the moisture in the water vortex tube. So again, we used compressible interfoam for that, and we see that after some period of time, the moisture is getting dispersed easily in the vortex environment. Okay, so this is easily can be explored in the compressible interfoam solver. So next application we have here is the typical problem which would have studied or seen, like we have a water can. Emptying the water can, you know that bubbles are rising up. So here we have a top can, the water emptying into the bottom can. So water is slowly rising in the bottom. And what is the beauty in this? We have simply used interfoam solver. It can easily capture the interface, but the beauty of using interfoam with respect to educational platform for teaching students, like inertial frame of reference and a non-inertial frame of reference. So I explored it with the help of OpenFOAM solvers. Interfoam solver has also got rotating frame of reference like MRF foam. You can also use that. So relative frame of reference, it is being taken care of. And the difference between inertial frame and non-inertial frame is that, so you have typically inertial frame like using these equations at the bottom, like the momentum equations and the continuity equations. Whereas in the UI stands for inertial frame velocity, whereas UR is a rotating frame of reference velocity. The connecting thing is nothing but you have the equation like this: UI vector is equal to UR plus omega cross R. What is omega cross R? Is nothing but the Coriolis component of acceleration, Coriolis component of velocity. Okay, so here we explored it. Already the solver is being embedded with the Coriolis component in the MRF solvers, relative frame of reference. Okay, they have solvers in the interfoam also. By simply enabling that, we could see that we could understand how the volume fraction changes in a non-inertial frame of reference. That is, in this case, it's a rotating frame of reference. So you can easily see the difference between the interfaces in the inertial frame of reference and a non-inertial frame of reference. So we can also see the velocity. How does it change in a interface like air-water interface in both the top and the bottom containers? Using this between frames of reference, between two frames of reference. So I think with this, I would like to come to the end of my presentation, and more you can see at this. You can see at my website also. Thank you for listening, and if you have any questions, you can also ask here or give me a mail at manimaran@bat.is. Thank you, man. Thanks for giving the opportunity, and I would like to extend thanks to our CFD FOSSEE team also for coordinating this.
Yes, sir, the pleasure. It was our pleasure actually.
Thank you.
So, any questions for Professor Manimaran?
Yeah, I think one question is already there. I just spin that cover. How to inject or initialize the multiple bubbles? So bubbles, initialize multiple bubbles. Actually, I do not know what you're talking about. Whether you want to have different airflow rate at the inlet, or anyway, if you have different flow rate, you will see that many bubbles are coming. You can also see multiple bubbles. Injection at one point or multiple points that can also create multiple bubbles. Whereas even at injection at one point also, you will see that bubble is getting transported from bottom to top, or left or like horizontal, like vertical pipe, or like left to right and all horizontal pipe. Yeah. Any other questions you have? Another by Rajat, I think we can do coupled CFD DEM analysis, DEM analysis in OpenFOAM. Like my work focus on extrusion or solid reinforcements during 3D printing. So I think this is also possible. In one of my literature slides I've shown you, you can couple both of them using MPPIC and then multiphase intermixing foam is also available. Yeah, intermixing foam. So if there are no more questions, thank you for giving this opportunity, ma'am. I think the next section is on tutorial, I think so.
Yes, sir. So thanks a lot for joining and giving and sharing your valued experience about this subject. And I think all of them have enjoyed the session. Please feel free to write to him directly, or you can also write to us at contact-cfd@fossee.in. So later on, we can connect you to Professor Manimaran, and then your doubts can be cleared. Okay.
Okay, thank you.
Thank you, sir. Thanks for joining.